Today we are going to learn how to generate and play sound waves. For that we are going to import some of the libraries. In the first cell we have mentioned those. Now our target is to generate a sine wave with certain components. So for that we are going to define some of the variable, like we are going to define at what frequency this sine wave will operate, how many samples will that wave will have, and the other parameters like sampling rate and amplitude. Now once we have defined our parameters, we can plug those into a formula to generate sine wave. So what we have done here is we have iterated up to number of samples like 48,000, and then at each iteration we are going to apply this np dot sine 2 into pi times frequency, which has been present here, and the sampling rate. So this will generate our sinusoidal sine wave. So now we need to store that wave into an audio file so that we can use it later. So for that purpose we are going to use the library wave. So we need to define some of the parameters first. So we have defined parameters like number of frames, compression type, compression name, number of channels, and sample bandwidth. You can find description related to these parameters into my earlier video, which is filtering noise from audio file. I'm going to mention the link in the description. So for now, once we have supplied those parameters, we can just call our library and write the data. So writing data, what we are going to do is we are going to convert integer into binary format, because files are stream data, they are not integer in nature, so they will be like 0 and 1 kind of a. So for that we are going to use a struct library, and a pack function responsibility is to convert that integer into binary. So once we have written the data, we can just directly play that file. So for that we can use the ipython utility, which is ipython.display.audio, and mention the path of the audio file. So let us play this, and let me set the sound to maximum. As you can see, there's a very sharp sound, a beep sound like ping, something like that. So this is the sound of a sine wave. You can generate cosine, tan, or whatnot. You can generate any random sample based on this description. We just need to make sure that this variable sine wave contains the list of integers, and you can generate any sample with it. So now so we have generated sample, but how we are going to visualize that? So for this experiment, our aim is to generate and visualize the sample. For that, what we are going to do is we are going to use a DSP utility called Fourier transform. So the purpose of the Fourier transform is to convert an analog signal into its frequency part. Like we have a time domain signal. So what it's going to do is it's going to read the time domain signal and convert into frequency domain, so that we can visualize it much better. So once I'm going to show you the diagram, it's going to be much clearer. So for now you can just see like go with the flow. Like here we are going to mention the audio file which we need to pull, the number of samples, the wave. Utility is going to open that audio file, and then we can just convert those binary data back to integer. This is a reverse of exactly what we have done earlier. So now once we have done that, we can use that np.absolute to get the frequency component out from that file. So once we have the frequency component, the thing with this array is that at each index it denotes a certain frequency. So at index 1 it is pointing to frequencies 0, and similarly 1000 pointing to frequency 1000, something like that, and similarly other. So what's happening here is that we are going to look like at different indexes in this array what value we are getting. So we have plotted some of the values, and as you can see, the number of frequency at or number of value at 1000 frequency is much higher compared to other. So which should be the case, because initially we have set the frequency to 1000 as you can see here. So this ensures that we have got the signal exactly what we wanted. And there are some trade, like there's some minor values in other frequency, but that should be the case because nothing is absolute here. Like the when you convert a signal, there's all some lags and or kind of error rates. So after that we can just plot this values. So we have two plots. One is in time domain, which is present here, which is this nice looking sinusoidal wave, and the other one is a frequency plot which we have obtained after applying Fourier transform. So it shows that like at what frequency is present in our signal. As you can see, only one frequency is present, which is 1000. All other are minute or approximately equal to 0. So this is how we can generate any signal, and we can just visualize it. I'll be posting all the links in the description for further analysis.